As we mentioned in our last video on electric potential, this is an extremely hard concept to grasp in all electricity, but we're going to keep going here with a little bit more of introduction. So I'd like to draw some more analogies to gravity in this video here to give you hopefully a bit more intuition about what electric potential is about. So let's just start with a little analogy with gravity like this here. Suppose I had the ground right here, and I had a ball right here at some initial point, and the ball was sort of thrown up so it reaches some final point like that. So the ball is sort of given some velocity this way by someone throwing it. So what we notice about the ball, of course, if you throw a ball up against gravity, of course it slows down because it's going up against gravity. So what I'll sort of get out of this here is the change in kinetic energy of this ball is definitely going to be less than zero because it's slowing down. But it's getting higher above the ground, so the change in the potential energy of the ball is going to be greater than zero. So where kinetic goes down, potential goes up. But there's also sort of another adage from mechanics that says that if you want to change the potential energy of something, you have to work on it. So work here is the change in kinetic energy. Okay? So this means by if the kinetic energy is less than zero, then the work must be less than zero also. Okay? And so then the next case here, exactly the same case over here. Suppose the ball was up here. This was the initial case, and it went down to the final case right here, and it was given some v like this. There's its velocity now. So there's initial and final cases. This is supposed to be a v right here. So it's given some downwards velocity. Now what we know about gravity is that when you throw a ball down, well, the change in kinetic energy is going to be greater than zero. The change in the potential energy is going to be less than zero because the ball is getting closer to the ground. But because work is the change in kinetic energy, the work is going to be greater than zero also. So see, we have these two cases here. We're just sort of analyzing what happens when you push a ball up against gravity versus down against gravity. Okay? And so we have a couple things like that going on. But because of the way the signs work out here, because work is the change in kinetic energy, say in this case here, what the kinetic energy loses, the potential energy gains, but the kinetic energy lost is just the work done. So if I sort of tie all these things together here, there's another sort of bit from mechanics that says that work then is minus the change in potential energy. So work is two things here. It is the change in kinetic, but because of the way kinetic and potential exchange energies as balls fly, these two relationships sort of hold here. So the next thing to get at then, again with the gravity analogy here, is we know that when a ball is so high above the ground, a distance h above the ground, we know its potential energy is mg times h. But the question then about the mgh is where does this come from? Where does mgh come from? So let's just go back. So here's a ball, and here it is on the ground. There's a ball on the ground. And suppose I want to lift the ball up to this distance here, which is a distance h above the ground. What do I have to do that? Well, I have a couple of relationships here, and let's see if I can tie those in and maybe get an answer. So really the only thing I know at this point here about this system here is that work is the integral of F dot dr, or work is force times distance, but this is the integral form of it from calculus, so you can sort of work it this way. Now if you look at the problem here that I'm doing here, is that I'm trying to move the ball up like this, so the dr for this is going to be up. But of course gravity, the force on it, is down. Down like that. So the work that I'd expect gravity to do on the ball is the integral of mg, which is of course is down, so I'll put that in the minus y hat direction, dotted into dr, which is in the positive direction here. So because the force is down and the push is up, I'm going to generate a minus sign, so I'm actually going to get here that work is minus mg times y. So I'm almost there, but this isn't quite potential because of this minus sign in here. But as we just discussed up here, work is negative the change in potential energy. So then the change in potential energy I'll get for this will be mgy. And this is the nice familiar result here, but that's where it comes from. So the reason why I want to do that here is because let's do the exact same thing now, but only for that proton in between the plates of a capacitor. Let's see if we can get a relationship like this for a proton in between the plates of a capacitor using all the things that we have here, because some of this stuff doesn't change here. In fact, maybe we'll jot down some of the relationships here. So we know from gravity here that delta U is mg times y. We know that work is the change in kinetic energy, and we know work is minus the change in potential energy. So just a few relationships there that we'll borrow from the bit of the board that was erased. But now let's hit that proton between the capacitor plates, something that has to do with electricity. So here's the lower plate. We'll put a bunch of negative charges on this plate right here. And here's the upper plate. Put a bunch of positive charges on it like this. And we'll do the same thing. We'll put the positive charge down here. because we know the charge would like to stay down there because it's close to the negative plate right there. So opposites attract, so it would like to stay there, just like the ball, when it was near the ground, would like to stay near the ground, but we're purposely going to lift it now. Okay, so what we're going to do is we're going to try and push the proton up this way. Now, where's the force? Well, we know it's going to be attracted down to that lower plate, so what we better do is draw some electric field lines in here, because we know those are things that exist between these two plates like that. So there's some electric field lines like that. Let me get that positive charge back on there again. And so the blue line, of course, is the direction that I want to push the ball, something like that. But I know now that the electric field lines, whereas that pink color, are down like this. And protons always like to follow with their positive charge, given that F is equal to QE. The protons always like to follow the electric field line. So the electric field lines are down, the proton would actually like to go down also. So when we're going to do this idea here that we did last time, that work is the integral of F dot dr again. We have a very similar situation with the ball here. We know that the force is down, so we can put an integral in here. This is going to be Q times the electric field dotted into dr. But let's make sure we get our signs right in here. So what we have here, we'll pull the Q out because it's a constant, but we have the integral here. Now what E do we have? Well, it's going to be some E naught, and you can look up in a previous video what that is, but we know the electric field points down in a negative y-hat direction, and we're dotting that into a dr, which is in the positive y-hat direction. So E is down and dr is up. So what that's going to do is generate a minus sign for us here, and we'll get QE times y, but it's going to be negative. So then the work done on the proton by the electric field is negative. That's what we got. But now we know up here from some of our other relationships here that work is equal to minus change in potential. And so we can sort of work on that. All right, fine. So that means the change in potential energy of the proton as it went from here to here is just QE times y. Again, let me make sure we know what y is here. Y is sort of the distance that we move the proton, almost like the distance that we lifted the ball. So we might have lifted the ball a distance y above the ground. Well, we're moving the proton a distance y above that negative plate right there. Something like this and that. So there we go. So delta U is QEY. So we have a nice result here. This is a change in electric potential energy. And just by analogy, remember the same thing for gravity was m times gy. This was the gravity result. Both of them talk about change in potential energy. This is gravitational potential energy down here. So we have some two very nice analogous results. And that's just what happens when a proton moves in between the plates of a capacitor. But the issue then is like, where do those volts come from then? So let's just go through something one more time. Let's add this result to our list up here, because now we have a nice result for electric potential. We got Q times EY, all for this proton moving in a field. Let's erase this, and we'll just look at one more thing as we wrap this video up now on electric potential. So there we go. So these are all sort of the relationships that sort of came up in the context of this discussion here. This is sort of our nice and new one right here. Really happy to have it now, because we sort of have something that's related to the potential energy of a charge, something that has to do with electricity now. So what do we want to say next about? Well, where do the volts come from? Well, it turns out that if you look at these two expressions right here, there's something you can do here, which is really where the volt comes from. Over here, the gravitational potential energy, you have m times g times y. And what you can do if you want, you can actually divide that u by m. It doesn't make much sense to do this, but we're going to draw an analogy with this. And so what this sort of tells you then is that by dividing by m, this term over here sort of tells you that doesn't really matter what you lift up against gravity. So whether you're over here, whether you lift a small ball up or a huge truck up like this, if you lift the ball or the truck up like this, this thing is telling you when you divide by the mass that there's still some constants in this process here, because g never changes. That's 9.8. And if you lift these things up to the same height y here, y doesn't change either. So sort of like the potential energy per unit mass as it was lifted like that. And believe it or not, that's exactly where the volts comes from here, because the change in potential energy here is QE times y. And if I divide this side, the u, by the q here, and get E times Y in here, it turns out that this side over here is the volt. The volt then is E times Y, and this is in volts. So for the first time, we have something that really feels and sounds like we're doing something with electricity. That's where voltage comes from here. And where it really comes from is moving a charge some distance around in an electric field. And we sort of discussed this just a tad bit before when we spoke about that proton in between the plates of a capacitor that was charged up by a battery, or maybe it was in the previous video here. So what we have here is if we have a bunch of negative charges down here and a bunch of positive charges up here, we might consider, well, how did this happen? And as we discussed, it turns out you can get a system to charge up like this using a battery. So that's positive and that's negative, and this is a 9-volt battery. It would charge up and look like this. There you go. There's a 9-volt battery. Now what happens next then is that we know there's an electric field between these plates like this, down, away from positive, towards the negative like this, always points down like this. Now what we can do is if we put that proton back in the field here again, the proton's going to be right here. Now we would very much like to stay near this negative plate because just the basic force law that we know, but if we sort of grab it and try and push it up against its will here, we know what we're doing. This is 0 volts and this is 9 volts because that's the way the battery has held the thing. And if I lift the proton up here to this point right here, what have I done? I've lifted it a distance y in an E. And that's exactly what this relationship sort of tells us here, that the voltage that you can sort of give or impart to that charge now is E times Y. Take that electric field, multiply it by that distance that you moved it, and that will tell you how the voltage has changed as it's gone up. So a little bit bad in my notation here, but if we have a delta U over here, this should really be a delta V, and this should be a delta V right here. It also stresses the fact that voltages are never absolute. They're always some relative measure. This is a V, not a U right here. So that's sort of what happens here. And I'll just reiterate one more time. If you move a charge a distance in an electric field, the potential difference or the voltage that it will incur, experience, have, whatever, is just that electric field strength times the distance at which you moved it, these two parameters right here. So that's sort of in a nutshell then what voltage is all about. It's about moving charges in fields. Maybe we should even summarize that here. So volts is really about moving charges in E fields. That's sort of where the volt comes from. So we need to discuss or quantify then what properties of the charge has changed as it moves around. And one thing we know for sure is that the voltage can change when you multiply E times the distance that you moved it, either parallel or anti-parallel to the field. So that's it sort of for an introduction to electric potential. That's what the volts is. So now you know you're doing something with electricity now. It's the volts here. But what volts are really about, where they come from, are charges moving in electric fields. That's sort of where voltages come from.